Okay, now we will analyze the ball's motion using Tracker. For starters, we're going to define the axes that this ball's motion will be observed on. This is the positive y, this is the negative y, this is the positive x, where most of the ball's motion will take place. This is the negative x, going into the screen is the negative z, going out of the screen is the positive z. And for a length reference, there is a 0.3048 meter long ruler right here on the screen. As you can see over here, the time is tracked for each position. Time begins at 0 seconds and ends at 0.667 seconds. Also, the ball's positive x position is tracked here and here, and it begins at 0.114 meters and ends at 0.992 meters. And now we will watch the ball travel at a constant velocity. There we go. These points are tracking the center of mass of the object, and then those points are plotted on the axes over time and used to make this chart. These values will be used later to compare to the computational or predicted model that we made using Python. Now we are going to predict a ball's motion at constant velocity using a Python code. And we are using some of the initial values we had from before in our tracker video. And here are those values. The ball's mass is 0.143 kilograms. Here's the ball's initial position vector, 0.114 meters in the positive x direction. Here is the ball's predicted initial velocity. We found that using the first 2 points of our tracker video. It is 1.66 meters per second in the positive x direction. Also, it began at time 0, and it goes until time less than 0.667 seconds. Also, just the physics of this code, we're going to use the momentum principle or Newton's second law, and that can be simplified to be final velocity equal to initial velocity plus the net forces on the object times the delta t over the ball's mass. However, since the ball's net forces are 0 and it's moving at a constant velocity, this will go away and the velocity will always be the same, and hence the reason we have a constant velocity, because these are our only two factors. This is how the model will predict the ball's position. This formula, another physics formula we're all familiar with, the RF equals RI, that's the position, plus the ball's velocity times delta t. And t, of course, equals t plus delta t. And now we can run this and predict the motion of the ball. Okay, so here is the origin, and this is the beginning point of the ball's motion. As you can see, it goes over this far in the positive x direction. It does not move in any other direction. Here's a graph of the ball's motion. Begins once again at time 0 and ends at time 0.667 seconds, and it moves the amount we expected it to as before in the positive x direction. As you can see, this line has a constant slope, and on a position versus time graph, the slope is the velocity, so that confirms our observation that the ball was moving at a constant velocity and has no acceleration. This chart shows the object's position used in the model, which we used Python to create, and this blue line shows the actual observed position that we found using Tracker.